Let's take a look at our notes. In the reactions, you should be able to click on reactions somewhere. I don't even know where that went. Under the participants tab, I think. Maybe not. I don't know where to find it. If you can, give me a thumbs up if you can see the lecture notes, or if you happen to have your camera on, throw a thumbs up in front of that camera. Awesome. Sweet. Thank you so much. I recorded the wrong thing the other day, so it's nice to be able to double check that. All right. The last time that we had gotten together, we had talked about, we did start section 5.3, right? We talked about independent events, a little bit about factorials, and counting things. So what we want to do is we want to move on to this idea of Bernoulli trials. And essentially what we're looking to get to the binomial distribution. Well, that's the title of the section, I guess, so that's relatively obvious. But we're trying to get to something called the binomial distribution. So we want to think back, what is Chapter 5 about? Chapter 5 is about discrete random variables. So we've been kind of all over the place as far as this section goes, and not talking about that yet. In order for us to talk about discrete random variables, finding ourselves back in that place, we're going to talk about these things called Bernoulli trials. Essentially, what it is we have an experiment that can result in success or failure, and that there is a particular probability for success, and then we go ahead and repeat the experiment several times, a fixed number of times, so 5 times maybe, and then we look at the distribution of how many successes there can be, right? If there's 5 trials, we could have 0, 1, 2, 3, 4, or 5, right? So there's 6 options, 0 through 5. We can have up to 5 successes, so then the number of successes becomes our discrete random variable. Again, pretty clear that it's discrete because there's only 6 numbers that could be obtained, and then random because it depends on chance, right? The probability of success for the individual outcome is, right, we have a probability associated to it, giving us probabilities associated to particular values of the discrete random variable, making it a discrete random variable. So what are Bernoulli trials? Well, again, a Bernoulli trial is an experiment that is repeated, where the only possibilities for results of the experiment are success or failure. So you do an experiment, 2 outcomes, success or failure. The trials are independent from one another, so as we move from one experiment to the next, right, it's always the same experiment, but as we move from the first to the second to the third and so on, then we end up with well, I got distracted there for a second. Okay, as we move from the first to the second to the third and so on, each trial is independent from the previous. So I don't care what happened the last time. It doesn't change what's happening this next time. And then finally, the probability of success remains the same from trial to trial. So nothing is changing, and they are independent. We'll see how these 2 things are slightly different, right? 2 and 3 we usually think of as the same. If they're independent, then it's not changing the probability of success. Yes, but we can also have situations where the probability of success would change still anyway. So we need these 3 things, 2 outcomes, success or failure. Each trial is independent. Roll a die. Whatever I roll on this one is not going to change what I could roll on the next one. And then the probability of success stays the same. I am rolling a 6-sided die, so the chances of rolling a 3 are still 1 out of 6. And when I move on to the next roll, I'm not changing it to a 12-sided die or something weird like that. That would change the probability of rolling a 3. Right? I'm keeping it the same die, so it's still 1 out of 6 there. All right, so that's the idea of a Bernoulli trial. We want to then take a quick look at a basic example of a Bernoulli trial, about the most basic example we can get, flipping a coin. We want to consider the coin landing on heads. So our experiment is we flip a coin. We're going to say that it's a biased coin, so there's an 80% chance that the coin will land on heads. And we want to approach this thing saying that we want to flip the coin 3 times, and then we're interested in particular finding the probability that it lands heads exactly twice. So set up for a Bernoulli trial. Are these Bernoulli trials? Well, we just have to make sure that it satisfies the 3 requirements for Bernoulli trials, right? There's only 2 possible results. Success lands on heads, failure lands on tails. So first condition is satisfied for Bernoulli trials. The second condition is that we have independence of trials. When I flip the coin the first time, that's not going to change what happens. When I flip the coin the second time, that's not going to change what happens when I flip the coin the third time. They have no impact on one another. They are independent. And the probability of success each time I flip the coin is right 0.8. It doesn't change. I'm not changing the coin. I'm not changing anything. So the probability of success also remains the same. So these are Bernoulli trials. So excellent. These are Bernoulli trials. The next thing we can do is we can talk a little bit about finding some probabilities. So if I think of let X be the number of heads obtained, then I'm looking for the probability that this discrete random variable takes on the value 2, because in 3 trials, I could have 0, 1, 2, or 3 as how many heads I get. So X is our discrete random variable. We're looking for the probability that it's equal to 2. And how do we do this? Right? How would we be able to obtain this particular probability? Well, in order to do that, we would have to be given essentially a probability distribution or some sort of a formula to help us determine the probability distribution. And we talked before about having boys or girls, and right, that was in section 5.1, I think. I'm not even sure at this point. I don't remember. Yeah, that was 5.1. That was 5.1 because 5.2 was mean and standard deviation. So in 5.1, we actually took a look at something that would be considered a binomial distribution there, actually. But here, let's see, we want to learn how to create the probability distribution without having to write out all of the things like we did in section 5.1. So in the case of binomial distributions, we have a convenient way to do that. We base it off of essentially the same method that we did the first time. It's an adaptation to clarify how we find these things. But what we can do is we can use a tree diagram to help us find the probability of getting exactly 2 heads. So here's a tree diagram for us. So this is how we create a tree diagram. When we have a tree diagram, we go ahead and we say that we're starting here. When I flip the coin, it could land heads, giving me a success, or it could give me a failure. Sorry, give me tails, give me a failure. There's an 80% chance that I get success, 20% chance that I get a failure. Excellent. Now, if I landed heads, then I could, on my second flip, land heads again, or land tails. If I got in tails, I could land heads or tails for my second flip. And of course, I can, after my second flip, each of these can be split as success or failure, heads or tails, heads or tails, heads or tails, heads or tails. So what I end up with is success, success, success. There's 3 heads. And so there's 3 heads. I could have success, success, failure. That gives me 2 heads. I could have success, failure, success. That gives me 2 heads. Success, failure, failure. That's 1 head. Let's see here. Failure, success, success. That's 2 heads. Failure, success, failure. Failure, failure, success. Failure, failure, failure. So these give me my how many of the things I'm interested in happening. So these are how many heads I obtained. 3, 2, 2, 1, 2, 1, 1. Oh, I wrote 1 there, but there are 0 heads actually. So we can create a tree diagram that tells us, hey, these are all the possibilities. And we could have done the same thing back in section 5.1 for first child, second child, third child, and then call being a girl a success. So we could do the same thing there, and it would give us almost exactly the same thing. except I think there were 4 children, so it would have been an even larger tree diagram. So this gives us the number of heads. Now, the probability of this specific outcome, success, 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 can be found by multiplying the probabilities of success, right? The probability that we have, success and success and success. Because these things are independent from one another, I'm going to see if I have this written down on our very first page. So let's go back here a little ways. I don't have it written down here. Let's see here. Independent gives us, yep. I don't think I have this written down. So make sure you write this down. The important thing, the reason that we need to know that these are independent, or one of the reasons, and when we have independent events A and B, right, or A comma B rather, then the probability of A and B can be found as the probability of A times the probability of B. So this is one of the things that we want to use from independent events. Being able to multiply the probabilities gives us here that the probability of success is computed as the probability of success times the probability of success times the probability of success, which is exactly what we have here. So the probability of success and failure is 8/10 times 8/10 times 2/10. Probability of success, failure, success is 8/10, 2/10, 8/10, right, of this specific one. But then what we notice is that this one gave us 2 successes, this one did, and this one did. So the probability of having a discrete random variable taking on the value 2 would be equal to, it happened in these 3 scenarios. So I have this probability, 0.128, this probability, 0.128, and this probability, 0.128. So these are the 3 scenarios. They are disjoint from one another, or mutually exclusive rather, because saying success, failure is different than success, failure, success. But I don't care about the order, right? They're distinct because the order is different, but I don't care about the order, so I include all 3 of them. So I can add all of these up, of course, and I have this written down as 0.384. All right, so this is one way that we could obtain the probability distribution, because I could then find the probability of 0, 1, and 3 as well to give us the entire probability distribution. But instead of creating this tree diagram, because, well, I could repeat the experiment 10 times. If I were to repeat the experiment 10 times, right, I don't want to create a tree diagram that's, let's see here, that's 1, 2, 3. So I need to do that 7 more times. So it would get doubled 7 more times, 2 to the 7th. Wow, that's huge. That's huge. It'd be like, see, 2 to the 4th is 32. No, 2 to the 4th is 16. 5th is 32. 6th is 64. It'd be 128 times larger than this. I don't want to draw a tree diagram that's 128 times larger. I want to know, how do I find this? Well, the reality is if I have 3, right, in each of these cases, I have 3 outcomes. And what I want to do is I want to have 2 of them, exactly 2 of them be success, but I don't care what order. If I want to find out how many ways I could have exactly 2 successes, what I can think of it as is, for the 3 outcomes, choose 2 of them to be successes. And that tells me exactly how many possible ways there are. So I can use binomial coefficients, the number of ways of counting. So for 3, I'm going to type this in. for 3 trials, I can simply ask myself, right? You would ask yourself, how many ways in 3 trials can I get 2 successes? Right, so that's what you would ask yourself. So essentially, you're saying 3 trials, choose 2. If I have 3 trials, choose 2, that's exactly the binomial coefficient 3, choose 2. So that's how many ways I can get exactly 2 heads. But I know that the probability of 2 success and 1 failure is 0.8 times 0.8 times 0.2, which is that 0.128 that we saw earlier. So the probability that our discrete random variable takes on the value 2 is exactly, well, there's 3 different ways that I can get this possibility, or this many ways. We'll see that it's 3. There's this many ways that I could get that probability. So I just multiply the 2. So I take 3, choose 2. Notice that this is 0.8 squared times 0.2 to the first power. And 3, choose 2 is 3. And then this thing is 0.128. And when we multiply those 2 things, of course, we get 0.384. So we can look at this a little bit differently than having to create a tree diagram. Again, if you needed to, you can evaluate 3, choose 2 by hand as 3 factorial divided by 2 factorial times 3 minus 1 factorial. So that's 3 times 2 times 1 divided by 2 times 1, and 3 minus 1 is 1, so that's just 1. Ones don't do anything, the 2's cancel out, and it's 3. So you can compute that by hand, or you can use a calculator. We'll talk more about how to use a calculator maybe the next time that we get together. Actually, you could just YouTube search, use TI-84 for combinations, right? Combinations, TI-84, binomial coefficients, TI-84, or 83, whichever version that you have, and that would be absolutely fine. So this is how we can use the binomial coefficients to help us compute probabilities. When we have a variable such as this one, we have exactly a binomial random variable. So this key fact we already talked about, the number of successes, number of ways we can have X successes is N choose X. So we already said that. And then this is exactly the formula that we used in our calculations. The probability that our discrete random variable takes on a specific value is how many trials, choose this many of them to be successes, the probability of success raised to the number of successes, the probability of failure raised to the number of failures. If you wanted to see, that's exactly what we wrote down right here. 0.8 times 0.8 is 0.8 squared. 0.2 is 0.2 to the first power. So you always take the probability of success and raise it to the number of successes, the probability of failure, raise it to the number of failures. And then how many ways can you have that many successes? So that's what they're saying here in this formula. Again, when we have such a discrete random variable, this is called a binomial random variable, and it has what's called the binomial distribution. Okay, and everything for the binomial distribution is determined by N and P, so it's said to have parameters N and P, right? How many trials? That's the number of trials, and that's the probability of success. All right, so we want to take a look at an example, but as we look at the example, we want to be led into it by considering the how do we know that we're working where we need to be? How do we find these probabilities? This is a nice outline. If you want to follow it along, that's exactly what we already did. But what we want to make sure that we have is first, Bernoulli trials. So the assumptions are that we're working with Bernoulli trials. Once we know that, of course, we've already determined the probability of success and the number of trials because we've already identified that we're working in Bernoulli trials. Of course, we've also identified what a success is. That's exactly what we've done here. So then we just apply the formula. So once we can observe that we're working with Bernoulli trials, then we are able to use the binomial probability formula for the specific values. And what I'd like to do is I'd like to, I think, maybe provide a supplemental video on, actually, no, not supplemental. Let's actually just go ahead and use it in this class or during lecture, because there's a way to use our calculator that's going to make things way easier. I don't want to do all these calculations by hand. I don't want you to do all these calculations by hand. We'll do some, not all. So let's take a look at an example. We want to consider a student taking a multiple choice exam with 10 questions, each with 4 possible selections for the answer. All right, so we're setting ourselves up here. It's a multiple choice exam, so we're only doing one thing, right? No, this gives us n, the number of trials. There's 10 questions on the exam. So if we assume that the student just guesses at each question, then we are now randomly choosing one of the answers. And with 4 possible selections, this gives us, right, if there's only one correct answer, probably there's only one correct answer, but there's 4 selections, then by the F over N model, P, the probability of success is one of the answers is correct, but there are 4 possible answers. So this gives us number of trials, probability of success. We know that since we're guessing from one question to the next, that they're independent of one another. We're assuming that one doesn't give the answer to the next. We're also observing that all of the questions are multiple choice with 4 possible responses. So the probability of success is staying the same. If one of them was a 5, right, had 5 possible responses, then this would no longer be Bernoulli trials, because for that one question, there would be 5 possible responses, giving a probability of success of 1/5. So multiple choice, 4 selections, gives the same probability for each. All right, so that helps us identify that we are working in Bernoulli trials. Right, we've verified the 3 things. 1, either success or failure, right? Getting the question right identifies with success. Trials are independent. One question isn't going to tell you the answer to the next. And then the third condition, so they are independent. And then for the third condition, there's 4 possible answers, giving us a probability of 1/4 for probability of success of 1/4 for each question. So it stays the same. We are working with Bernoulli trials. Now that we know we're working with Bernoulli trials, we can let X be the number of successes in 10 trials. So here's that number 10 coming up, right? I said I didn't want to make a tree diagram with 10 trials in it. Here's exactly a scenario where we would have to do that. Okay, success, failure. We don't have to outline, the four responses. We just have to outline success, I chose the right one, or failure, I chose one of the wrong ones. So if we want to find the probability that a student who randomly guesses answers, find the probability that they get a 60% on the exam, we're looking for the probability that the discrete random variable takes on the value 6, right? So they got exactly 6 questions correct on this exam. Easy enough. Easy enough. We can use the binomial formula. So we simply say there are 10 trials. I want to get 6 of them right. Probability of success is 0.25 or 1/4, however you'd like to write that. 6 successes. Probability of failure is 0.75, right? 1 minus 1/4 is 3/4. And this would give us 4 failures. So this is the probability of the individual possibilities, and that's how many possibilities there are of getting exactly 6 questions right. So when I say calculate this by hand, what I mean is we want to use our calculator to determine this thing, and this thing, write them down, and then multiply those together. So we're not doing it by hand entirely. Rather, we want to just apply the formula and use the formula correctly. So let me grab my calculator. And here we are. I want to be able to use this thing here. So I want to take 10 and go to math, and I can go to probability. I believe that I showed this last time. If I didn't, here it is, right? So 10, choose 6. This gives me 210 different ways that I can get exactly 6 questions right. 0.25 to the 6th power gives me a very small number. So I'm just going to leave this as 0.25 to the 6th. I'm not even going to change that. This would probably be a very small number as well. So when I say by hand, we're essentially looking for minimal computation. Throw it into your calculator. So I've got my 210 times the answer that I just found, times, I also need the 0.75 to the 4th power. And this gives me 0.02. 0.0205. Copy down as many decimal places as necessary. 260053. 260053. That's all the decimal places, so let's round accordingly. So here we have successfully found the probability that the student gets exactly a 60% on the exam. Now what we would like to do is we would like to talk about passing versus failure. So let's write the expression giving the probability that the student fails the exam. And we want to use appropriate probability notation. So we're essentially going to look at what's called a cumulative probability. So when I consider the probability that a student gets less than or equal to some specific amount, let's see here, make sure that I use that correctly. I believe it is less than or equal to that we would like. Yep, less than or equal to 5. Again, 6 would be passing. So if we're failing, then we got 5 or less. So this is called a cumulative probability because it adds up all of the probabilities for a specific number of successes and everything below, right? All the probabilities from 0 to 5. If I wanted to, I can I could recognize that this is equal to the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3. Oh man, I don't have hardly enough room here. Plus the probability that x is equal to 4 plus the probability that X is equal to 5. So I could calculate each of those individual probabilities using the binomial formula. But that would be a lot of work. So rather, what I'd like to do is I'd like to use my TI-84 or 83, whatever you happen to have. So if I want to calculate those things, rather than using the binomial formula for 1, 2, 3, 4, 5, 6 different things, I'll go ahead and I'll grab onto my calculator and I'll take advantage of the fact that the calculator is smart and can do the work for me. So one thing that we'll start with is actually going back to this example. If I were to say that I wanted to, let's see here, look at this binomial distribution. There's a button right here, distribution. So if I hit second vars, that gives me distributions. And if I scroll down far enough, let's see, I scrolled up to go down in this case, I have binom PDF. So I have the binomial distribution, and it's going to give me particular values. So this is a binomial probability distribution function. So I want to grab, if I wanted to, I could grab onto that. And if you have a TI-84, you'll get the option of entering these values. If you have a TI-83, it will just give you the function and you have to enter these numbers as comma separated. So we're working with 10 trials. I'm interested, I have a probability of success of 0.25, and I'm interested in having 6 successes. So I get this. Again, if you have a TI-83, you would have to enter those 3 numbers and then close the parentheses, 10, comma, 0.25, comma, 6. And this is the only thing you'd see if you have a TI-83. Once I hit enter, I can observe that somebody did something wrong, because this number does not match that one. See here. Oh, yeah. Okay. This one looks like it's supposed to be the right number. I must have done something wrong in my calculations here. Let me see if I can scroll back up and see what I did wrong. Ah, there, that's what I did wrong. Wow. Small mistake like that really changes things. So let me first say that when we did our work, we had essentially the right thing. I just copied a number in wrong. I can really mess things up. Here, this is the number we should get. So 210 times 0.25 raised to the 6th power. Let's see, delete that guy. And times 0.75 to the 4th power. And right, entering this number correctly, we should get that thing. Ta-da! And we do. So this was a mistake. I apologize. Let's copy some of those over correctly. 16,222. 0.016222, and then it was actually 0001. So we can do this by hand, or we can use that binomial distribution function in the calculator. But let's talk about our current example. If I remember correctly, we should be able to calculate each of these things, let's see here, by hand, and I want to I have answers written down so I can double check. I always need to make sure that I'm copying these right. So if I'm looking at less than or equal to 5, I can again use the distribution function. So distribution, scroll down or up, whichever you find convenient, to the binomial probability distribution. But I don't want probability distribution, I want cumulative distribution. So if I use CDF, the cumulative distribution, then I can give it just this basic information and it will do all of this addition for me. So I can use the binomial cumulative distribution. I'm still working with 10 trials. I still have a probability of success of 0.25. In this case, I'm looking for a maximum number of successes of 5. So when I enter the cumulative, it's going to add up all the probabilities for 0, 1, 2, 3, 4, and 5. It will add all of those up for me when I hit this. This should give us the right answer. Yes, excellent. 0.98, 0.27, 0.27. Copy as many decimal places as you need, 22,931. So I get a value for that. Again, I could evaluate each of these individually by hand. That's a lot of work. I could calculate each of these individually using the calculator and then add them together. Or I can use the binom CDF with 10 trials, probability of success of 0.25, and a maximum of 5 successes. And this is going to give me that answer. All right, we're looking good. We're looking good. We have a couple more parts to this example. So let's take a look at the probability that the student passes the exam. Now, there's a couple different ways that we could do this. Again, if I want passing the exam, I'm saying that the number of successes is greater than or equal to 6. So I could recognize that as the probability that x is equal to 6 plus the probability that is equal to 7 plus the probability that is equal to 8 plus the probability that it's equal to 9 plus the probability that it's equal to 10. So I have all these possibilities. I could compute these individually by hand, or I could, well, what could we do? This is no longer a cumulative probability because I'm looking at greater than or equal to 6. The cumulative is going to give me the specific number and lower, whichever way I want to point there. So lower than 5, like we did in the last problem, but this is greater than 6. So, man. Well, if we recognize that failing and passing are complements of one another, I could recognize that this is 1 minus the complementary event, right? The complementary would be less than or equal to 5. So in this case, I could add up all the individual or recognize the complementary relationship and then give this as 1 minus the number that I found before, 0.98, had a whole bunch of decimal places. I go back to my calculator. I have that answer still. So I can just do 1 minus answer and get my 0.01972. Let's see here, 77,069 are the other remaining decimal places. Of course, I'm sure that goes on for a while. So here we have our probability of passing the exam. So if you've got a 10-question exam and you're randomly choosing, chances are you're going to fail, according to this example anyway. So no bueno. Make sure you study so that way you don't have to randomly guess. All right. So we wrote an expression for the probability, and then we actually used our calculator to help us evaluate that. These are the sorts of things that I would expect you to do on the exam. If I give you a binomial random variable, and I ask you to compute some probabilities, I would expect you to use probability notation. And I would expect you to recognize the complementary relationship and use your calculator to find the cumulative probability. So I would expect to see this sort of thing, at least this portion of it. Same thing goes with this. Actually, with this one, since it's cumulative right away, all I would really expect to see is this. And then in this case, if I ask you to calculate by hand, I would expect to see, right, all of this sort of work. So make sure that you're aware of that as we approach the next exam. If you don't have that work written down, it can be difficult to assess your understanding. Of course, if you have a right answer, then for the most part, you should be okay to go, but I will grade on appropriate notation being used as well. All right. In part C, they wanted us to just evaluate these, and we already did that. There's one thing that I would like to consider as well. So this is kind of an additional example. If I wanted to find the probability that the discrete random variable takes on values between, let's say between 4 and, let's see here, let's say 7. If I wanted to find this, what I can recognize this as the probability that we get less than or equal to 7, but this includes all of the probabilities for 0, 1, 2, and 3. So I would have to subtract the probabilities for 0, 1, 2, and 3. And again, this adds up all the probabilities for 0, 1, 2, 3, 4, 5, 6, 7. I don't want the probability of 0, 1, 2, 3 included. So I subtract that probability. And then I can use my calculator to perform this operation. So I can go up to our, actually not that, I want our distribution. So I can go down to the distribution. See, use B in the future. Excellent. So I can use this. And if I look at a maximum value of 7, I can take that and then I can subtract. Actually, I can just go up here and grab onto this guy because that's a cumulative, and subtract where it's 3 or less and hit enter, and it gives me the probability of obtaining between 4 and 7 correct answers. So 0.2237. So that helps us right, evaluate these sort of expressions as well. All right, beyond that, it's just a little bit of a discussion on what these probability distributions look like. When we have in a situation where we have 6 trials and the probability of success is exactly 1/2, we get this nice shape that's almost kind of bell-shaped, and when we have a low probability of success, then of course we would expect to get a low number of answers correct. In this situation, we have a low number of successes. And when we have a high probability of success, 3/4, we would expect to have more successes. Excellent. So that's what our distributions would look like. Of course, I can find the specific values for each of these using our binomial probability formula. All right, so I said that there would be new versions of mean and standard deviation, and it's true for a binomial random variable. The formula that we're given in section 5.2 would actually simplify to these. The mean of a binomial random variable is simply the number of trials times the probability of success. And the standard deviation for a binomial random variable is the square root of number of trials times probability of success times the probability of failure. So we're able to calculate these much more easily than in the previous section. So if you're lucky, I'll give you this sort of thing on your exam instead of the other. All right. I'm not, if we wanted to, for our previous example, we could calculate the mean as 10 trials times the probability of success gives us a mean of 2.5. And the standard deviation is given by number of trials times probability of success times probability of failure, which is, right, let's see here, that's 16 in the denominator, 30 in the numerator, whatever that happens to be. Let's see if we wanted to evaluate that. We could. Looks like it should be 1.3693. All right. So we can calculate a mean and standard deviation very quickly, very easily. Ooh, okay, yeah, this is fun. So this is maybe not the most important thing ever, but it is really interesting and good to know. So when we are looking at sampling from a population and we're interested in a proportion, right? A proportion of the population that has some particular characteristic. When we are sampling with replacement, then the distribution of our possible samples, possible proportions, is going to be exactly a binomial distribution, okay? So suppose that a simple random sample is taken from a finite population with the proportion of members that have a specific attribute being P, then the number of members sampled that have the specific attribute. Okay, so if we were to randomly select and consider the possible values, then these possible values has exactly the binomial distribution. And then it has approximately the binomial distribution if we sample without replacement. If you're interested in knowing, I believe this comes up as a question on the homework. If you're sampling without replacement, then it's not exactly the binomial distribution. Rather, it is called the hypergeometric distribution. So that's a nice little tidbit to know. Again, I believe that's in your homework that asks that question. So then we have, it's close enough. Okay, we say that the hypergeometric distribution is close enough to the binomial distribution when sample size does not exceed 5% of the population size. Again, we're not too worried about that. It's good to know, so there's a homework question on it, but this is not necessarily used as we move into our projects for this semester. So we don't have to worry too much about that. All right, that is very conveniently the end of section 5.3. So that's it for me and it for our time. So make sure to take a look at those. Oh, no additional exercises. That's absolutely fine. But that's all that I have. So if you have any questions, just stick around and ask. If you don't, have yourself a wonderful day.